Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to be talking about Section 9.3, Separable Equations. Up to this point, we've discussed how to deal with differential equations in terms of how to graph them, how to plug in point values, and solve for some initial value problems, at least to some extent. But we haven't really talked about how to actually solve for an equation or a family of equations that would be the solution set for a differential equation. That's what we're going to be talking about here in section 9.3 and in 9.5. We're going to be talking about how to deal with some first-order differential equations. And then after Calculus 2, you'll deal with more differential equations in the actual differential equations course. But for here, we're just going to get started. And to start off with algebraic manipulation or algebraic solutions for first-order differential equations, we're going to talk about a very specific type. And that type we're going to talk about are what we call separable equations. Separable equations are just that. They're equations that you can separate the x values and the y values, or maybe the y values and the t values. You can separate all variables of one type on one side of an equation and all variables of the other type on the other side of the equation. They tend to look kind of like this. For example, the first one is dy dx equals gy times f of x. So I have two functions, one in y, one in x multiplying, and then on the other side I have the differential. Or if I already have the differential splits, I have some amount of y times dy and some amount of x times dx. These are really nice because all I really need to do in order to solve these is to get it like in this second form and take an integral of both sides. That's all I really need to do. And then what I try to do after that is solve for y equals if possible. There are going to be some instances where we won't be able to necessarily do that to get y equals by itself, but if we can, we will always try to. Usually if there's a lot of different functions multiplying y or operating on y, then it may be difficult to get it by itself, but we'll always attempt to do so. And one other thing to keep in mind with this, because we're going to do an integral of both sides, our solution really for this one would be g of y capital plus c equals capital F of x plus c. So we'd have an arbitrary constant come in on both sides. And typically what we'll do is just combine them, because this would really be constant 1 and constant 2. But if we just subtracted constant 1 over, we would just get a different arbitrary constant. So we would have to add that to the other side. So we will still have technically two different constants, but we'll combine them all to one side just for simplicity's sake. So you'll very often just see a single constant like that. Okay, so that's basically all we're going to be dealing with here. And most of the integrals that we have in this case are really what I consider as baby integrals, particularly with what we were just talking about in Chapter 7 and Chapter 8. All those integrals were far more difficult than most of the ones that we're going to see here. Most of these should be pretty easily solvable using usually just u substitution. So let's do a couple examples, and we're also going to do some examples here that have initial value problems, where we'll be able to solve for what that unknown constant is supposed to be, given the points of the initial value. So we have example 1 here. We have solved the differential equation dy over dx equals negative 4x y squared, and we're going to find the solution of this equation that satisfies the initial condition y of 0 equals 1. So that means when x is 0, y is 1. With those coordinate points, we should be able to solve for the arbitrary constant that comes out of this. But let's see what we can get. Now, again, note that this is going to be separable because I have some amount of x's multiplying some amount of y's, and I just have a differential on the other side. I should be able to split this up appropriately. dy dx equals negative 4x y squared. I should be able to split this up appropriately so that the y squared bit can move to the other side, while simultaneously the dx part will move to the right side here. What you are going to always have to keep in mind is that the dy and dx should always be on top of a fraction or on the numerator whenever you're about to solve with integrals. Do not have a solution that has dx or dy on the denominator of anything. So if I move these over appropriately, if I move y squared over, what I get is y squared dy. And if I move dx over, I have negative 4x dx. Nice and easy. And now at this point, I should be able to do an integral of both sides. Well, the integral on the left-hand side of y squared, that's pretty easy. That'll just give you 1/3. Oh, that's not going to be y squared, sorry. That's going to be 1 over y squared. Okay, still not too bad. That'll give you negative 1 over y, because I divided y squared over. And then the negative 4x, when I take an integral of that, that'll give me negative 2x squared plus c. I can multiply both sides by a negative and just have 1 over y equals 2x squared plus c. C is an arbitrary constant, so I multiply that by negative 1. It's still arbitrary. And then to finish that off, I can flip both sides, take the reciprocal, and I get y equals the reciprocal of the other side, 1 over 2x squared plus c. Note that in this case, when I took the reciprocal of both sides, that did include the plus c. This is something that's important to know. That means that you do not just want to solve for y and then slap on plus c at the end. You want to make sure that c is included the second you evaluate an integral. Now that we have this solved, though, we should be able to find out what c is supposed to be by using our initial value. We have that if x is 0, y is 1. So if I plug in those values, y of 1, 1 over 2, and I plug in 0 here. So I plug in my initial value. 2, 0 squared is 0, so I get 1 over c. So 1 equals 1 over c, which means that c is 1. Therefore, this solution is 1 over 2x squared plus 1. And that would be it. Alright. See? Not too shabby. Look how easy those integrals were to deal with. There's some manipulation in terms of algebra, but overall, it shouldn't be anything too terribly complicated. Separable equations are the best you will want to look for. Let's do another example. I have solved the differential equation. This one looks a little more complicated. The square root of 1 plus x squared over 1 plus y times dy dx equals negative x. All right. So notice again, we want to make this separable, so we want to combine all variables of one type on one side and all variables of the other type on the other side. And then we're going to solve this using the initial condition of y0 equals 2. Already, I have dy on top. So I'm probably going to keep dy and y's on the the left-hand side there, and the other variable, dx, I'm going to move to the right-hand side. So since I see dx on the bottom, that indicates that the dx's should be flipped over to the other side. So then if I do that appropriately, 1 plus y and dy are going to stay over here on the left, so we'll get dy over 1 plus y equals... And if I multiply the dx over and divide the 1 plus x squared in a root over, I get negative x dx over the square root of 1 plus x squared. And that I can take an integral of. The left-hand side's a little bit easier. That's basically just a 1 over u situation. This is going to give me natural log of 1 plus y. The other side may take a little bit of manipulation because you can do this as a u sub, or if you want to do trig sub, it would also work, but would be unnecessary. You could do u is 1 plus x squared, du is 2x dx, so that means du over 2 is x dx. So that means we're going to have that negative 1/2 on the outside here, of du over the square root of u. And we're going to have a plus c when we get that integral done. So that'll give us natural log of 1 plus y equals, this will give me 1/2 times 2 square root of u. 2 because I would then have to multiply by 1 over 1/2, which is that, plus c. So I have natural log of 1 plus y equals the square root of 1 plus x squared plus c. Alright, now I'm not done. Again, I want to see if I can get y by itself. Even if I can't get y by itself, if that does come up to be a situation, I should still be able to solve for c. But in this case, I only have a single y, and it just takes a little bit of algebra to get y by itself. First, I will take both sides as powers of e. That way I get rid of that natural log, and I'll have 1 plus y equals e to the square root of 1 plus x squared plus c. Note that the plus c is still in the exponent up there. That's very important. Remember that we don't just slap on c when we're done, we slap on c when we finish doing the integral. However, when we have an addition of things in an exponent, so this plus this, if this was even a plus b, I can rewrite this as e square root of 1 plus x squared times e to the c. That's the same thing as adding those exponents. And e to the c, where c is a constant, e to the c will itself be a constant. So that itself is an overall constant. So I'm just going to replace e to the c with an arbitrary constant, c. And then since I still have 1 plus y on the other side, to get y by itself, I simply need to subtract 1. So that would be the general solution. This trick of e to the c being a constant is going to be a very common one. A lot of these examples you'll see will involve situations where you take e to both sides, and you'll end up with c as an arbitrary constant. So get used to seeing that stuff. Now when we satisfy this condition, we plug in x of 0, y of 2. So that means we have 2 equals c e to the 1 plus 0 squared is 1 minus 1. So that means if I add 1 over and divide by e, I get 3 over e, or 3 e to the negative 1 is the same thing as c. So then when I plug that in, I get 3 e to the negative 1. I can put back into that exponent now. That's going to add a negative 1 to the exponent. So I'll have square root of 1 plus x squared minus 1. That would be the general solution. If c ended up just being a constant by itself without an e, I would have just kept it there. But because that would have been an e to the negative 1, I just combined it with the exponent up top. Oh, wait, hold on. Yep. Forgot about that minus 1. Minus 1. Okay. Alright, that's better. I was thinking about if you plug in x, you don't get 2, you get 3, but minus 1. Yeah, forgot about that part. But there we go. That should be the rest of it. Alright, now let's do the last problem here. Yeah, most of these, the integrals aren't bad. It's just some algebra manipulation after that. We have one more. Solve the differential equation. Quantity 2 plus 2y squared y prime equals e to the x y. We want to find the solution with this that satisfies the initial condition, y of 2 equals 1. So yet again, we already have this recognizable as splits, but we have that y prime. Remember that y prime is dy dx. So I'm going to write it as that. So 2 plus 2y squared dy dx equals e to the xy. And the position of dy dx should tell me where all the y's and x's are going to go. Since this is on the left-hand side and dy is on top, dx needs to move to the right. And so I want to combine all x's on the right and all y's on the left. Which means I need to divide the y over, multiply the dx over, and I get really 2 plus 2y squared divided by y dy equals e to the x dx. I can do the integral of both of those now. 2 over y is just 2 over y, plus 2y squared over y is just 2y. dy. And then I have the integral of e to the x dx. That's going to be a nice and easy one. But the other side, I'm going to get 2 natural log of y plus 2y will become y squared equals e to the x plus c. Okay, remember, yet again, do the constant after you evaluate the integral. So right after you're done with the integrals, you should have a constant on one of the sides, typically the side with x. Now looking at this situation, I have 2 natural log of y plus y squared equals e to the x. That is very, very difficult to get y by itself. In this case, I don't think it's exactly possible. So this is really as far as we're going to go with the general solution. If you want to divide the 2 over, you can. Maybe get natural log plus 1/2 y squared equals 1/2 e to the x plus c. You can do that, but this is good enough as a general solution. However, even if we can't get y by itself, we still should be able to solve for c using my initial condition. So with my initial condition of x is 2, y is 1, I should be able to get 2 natural log of 1 plus 1 squared equals e to the 2 plus c. Well, natural log of 1 is 0, so I just get 1 over here. So I have 1. If I subtract e squared, I get what c is. So then I can write my general solution as 2, or my solution for this specific problem as 2 natural log of y plus y squared equals e to the x plus 1 minus e squared. And that should be good enough. All right, so that would be the equation that solves that specific initial condition, and then you can always plug values back in and make sure both sides equal to each other. So it should be pretty easy to check. But with that said, that's really it for separable equations. I know this is rather short for this section, but this is really all you need to get down. Just know to split to both sides, take integrals of both sides, which shouldn't be overly complicated, and then solve for c if necessary. If you have any questions, feel free to put those in the comments below, or ask your instructor directly. But with that said, I hope you have a nice day.